This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
All right. Good afternoon, everyone. Before we start, a quick announcement regarding the workshop 3. The reports will be due Sunday night, midnight. So that gives you a little bit more time. And then the subsequent workshop 4, I plan to post it tomorrow, latest, with the next week's set of slides, or at least first half of them. And then you will have 2 weeks for the workshop 4. The report will be due the weekend after the classes end, and because I cannot put a due date in SWOTWAC, so that's not allowed by regulation. Any questions before we start? No, I will. Yep. Okay, so let's continue the fun topics. We are talking about time series analysis, and the goal is to describe and predict. Of course, forecasting is an important task in this context. And this topic has been around forever. So therefore, there are a lot of methods, as I mentioned, a lot of classic filtering methods. Then you can also apply some form of regression to it if you treat it as a windowed problem. Then probabilistic models, I will talk about Markov chains. That's, again, a classic approach. You can look at the time series and treat it as an output of a dynamical system. That's where you go deep into system theory, control and signal processing. And then the popular deep learning topics like RNN, LSTM, and CNN. You can use neural networks for this task. So that's the modern data-oriented approach. So I kind of put some emphasis points. I will not make this about dynamical systems. You have taken enough subjects on that. I will touch the Markov chains, but in a rudimentary way, and the filtering also for complementary to make the discussion self-contained and including the basics. That's the idea here. So many people see the time series analysis these days, and then the kids jump to some LSTM. That doesn't make sense. You need to know a little bit of fundamentals of the problem, and you need to know a little bit of the classical methods to appreciate what you're doing with the modern methods. So Markov models, we will also use them next week when we discuss, next week mainly when we discuss the Markov decision processes as part of reinforcement learning discussion. So, but you have covered this in probability, right? So you know the Markov models. Yes? So, and then you have, did you do any hidden Markov models? No? Okay, and then did you do any Markov decision? Probably not either, right? So you did the plain Markov models. I will start with a reminder refreshment, and as I said, I will not go too deep into this. So we will not solve any problems or anything, at least this time, because you can spend the whole nice semester on Markov models, hidden Markov models, partially observable hidden Markov models, and so on. That's a big topic in itself, but it's good to have a solid overview of it. So it is a probabilistic and state-based model, right? And then we have this, when we look at the joint distribution for a sequence of observations, this is not even the Markov, this is just straight probability product rule. You can use the, this probable, if you have these observations x1 to xn, you can write the joint probability distribution of these observations using the product rule, using these conditional probabilities, right? So this is from the probability book before even the Markov chapter. And then the Markov property is the thing that makes it, Markov property is the core idea behind the Markov models. The idea is simply future states depend only on the current state, not on the events that occurred before it. So this is a first order Markov model. And then you have this essentially a sequential state evolution. So if I am at this state, then at this state, then this summarizes all of my history. It's a very powerful concept, right? State. And I think you must have done it maybe in control or signal processing. Maybe in signal processing, signals and systems. Yeah, so the state is a very deep topic. You know, revisit it every year, you will get a deeper understanding of it. So, the Markov property first order is also this. So the whole idea, very easy to say, but very deep to understand, is you summarize all of the past in the current state, and that's very powerful. Not on the events that occurred before. So if you have this property, and for a first order Markov model, then the probability of xn given all the what has happened before in the sequence only depends on, you know, this is the same as the probability of xn given xn minus 1. So that's why these you know, sequential arrows here. Also, I covered this in the birth-death processes in communication networks and queuing systems. Queuing systems have also this. If you take ComNets next semester, you will see that, or if you have taken it before. So this, you know, once you then plug this into the product rule from probability, this is the Markov property here. Maybe I should have put a nice, you know, red thing around it. Then the sequence joint probability distribution of the sequence becomes initial probability times the product becomes simply probability of xn given xn minus 1, and then you iterate from n equals 2 to the end of the sequence. So you get this equation. So that will play an important role in the subsequent discussion. Right? All right. So, and now these are the things, you know, let's visualize things a little bit. These are the things you have seen just to refresh your memory. So, for example, this is a two-state, you know, transition diagram or three-state transition diagram. You can have as complicated as it gets for finite state Markov chains. And then you have these transition matrices, right, with the probabilities, transition probabilities, and these would be the scalars. The probability of going from state 2 to 1, state 3 to 1, state 2 to 2, state 3 to 2, and so on, right? So, and then same here with the 2 by 2 case. Because you have two states, you can only go from the two states to the next, what happens next type of thing, right? The probabilities then evolve according to this. If you left multiply, then the pi's will be the row vectors. You can also right multiply, and then you get the column vectors. Then you need to transpose A. It's the same thing, just different way of writing it. And under certain conditions, Markov chain may have a stationary distribution. So as it moves around, you know, as you move around the states forever, then if it has certain properties, then you may have a distribution of which states you visit most, the probability of visiting a state. So that's the stationary distribution. You can solve it from this with eigenvalue 1, kind of the eigenvector corresponding to the eigenvalue 1. Right? So that's something you knew before, and were tested before in probability theory. Now this is the part where you haven't probably done. We come to the hidden Markov models, but the idea is quite simple once you know what Markov models are about. So now let's say we have observations, x, and then we introduce a latent variable, z. For each xn, we introduce a zn, which may be of different type or dimension, right? So that is the z's are the things that are behind the scenes, x are the things that I'm observing. All right? So, and assume that the latent variables form a Markov chain. So we end up with the state space model. So the z's evolve, and then whatever the z is, you observe something out of it. Right? So that could be also a probabilistic relationship. So the joint distribution for this model is then that. Okay, so that's kind of, we need to make it clear. So you have the latent variables. Latent variables are evolving behind the scenes, and x's are what you're observing here. Right? Exactly this diagram summarizes the story. And when we write the joint probability distribution for this model with the x's and the latent variable z's, using the product rule and Markov property from the previous slide, 2 slides before, you have this part which is essentially the Markov property of the z evolution, and then you have here the probability of xn given zn, and then these are the there's a direct dependency here, so you have the conditional probabilities that are multiplied. So if the latent variables are discrete, then we obtain a hidden Markov model or HMM. So that's the thing. So a bit more deeper into it. So in the hidden Markov model, we can also treat the latent variables as discrete multinomial variables. So essentially, this is all about, you see, I'm talking about z's here. All of the z's, in terms of the latent variables, it's just a Markov chain. Right? There is nothing different from a Markov chain in this slide. So because there is no x even here. So z's themselves, if you ignore the x's, z's themselves are, a standard Markov chain. Nothing different from what we have said in the beginning. So I follow this Bishop's. I also wanted to put this from Bishop's. If you read the book, one of the main books of the subject, the notation from Bishop, you can write it as a conditional distribution, probability of Zn given probability of Zn minus 1, given the transition probabilities, given the model, essentially. You can write it as such. So A is the transition matrix, as we have discussed before, and then the jk, so you do the sum, and then the exponents are the previous state to the next state, Zn minus 1 to Zn, and then the j and k are the indices that I'm kind of going through. So this is another way of writing this conditional probability that I will show in the next slide. And then, of course, for the initial case, the initial node has no parent node, so it's defined in terms of a starting probability vector. So because Z1 doesn't have anything depending to the previous, you need a starting point. So this provides the starting point. Maybe this next slide visualizes things a little bit better. So the hidden Markov model, transition probabilities in terms of the latent variables, it's just a Markov chain. So you have the probability Z and K is 1. Jk means at probability at time Zn, the K1 is 1, and the n minus 1, J1 in this is 1, based on this notation. So this is just the conditional probability, and then that's what I said originally. You can write in the matrix form, and this is what you have seen before. So the probability of going from one state to another state at a given time n. Right? So that's, again, another representation of these transition probabilities. And then this is the lattice or trellis diagram. So you go for this. This diagram has time, right? This doesn't have. This doesn't really have time. It is only states, and then you have the transition probabilities. Here, when you start from a state and then evolve with time in this n minus 1, n minus 2, n minus 1, and n plus 1 as time goes. Because it's simply 3 states, you are just jumping between the states, right? So you go from maybe one sample path could be I start from state 1, I go to state 2, then I go to state 3, come back to 2, and so on, right? So I can go like this, or another one like this. So it could continue unrolling it, right? So the question then is, now that I have a latent variable model and then there is a Markov chain of these latent variables, how can I predict the outputs, right? We can predict the outputs, or we can write an expression for these emissions. I have written this before, I just repeat it here. So there is this dependency, the conditional probability of having an output xn if the state is zn, right? So that's the dependence given a model phi. That means probability of xn given phi k, and with this is just a notation here, as I said, this k1 notation. And then the phi is the set of parameters of the distribution. This is just the parameters. And when you write this, multiply this with the z together, write the joint probability distribution given, in this case, I think I copied. In this case, I have actually theta as the more general set of parameters of both x and the Markov chain of the z's. So all of the parameters a and phi together make theta. So all of the parameters are here. So XZ joint probability distribution, given all the parameters, is the Markov chain of the Z evolving. That is something we have derived, right? The latent variables are just evolving according to the Markov chain, and they have a transition probability matrix A. That is the only parameter set that you care about for this case, and then multiplied by this, XM given ZM, and then this distribution may have its own parameters, because what type of distribution? It can be anything, right? So you are in a given state zk, for example, that then the xk that you observe from it, maybe it's a Gaussian distribution, right? So for example, in the Gaussian case, it may be that the being at a state zk that dictates maybe a mu k and the variance, sigma k, and then the x is a noisy version of it, noisy version of that mean. Remember, so this is the emittance business. So you have, at this point, then you emit something with a mean and variance as a Gaussian, and then this, you observe it with a Gaussian distortion. So it's kind of a distorted observation. You can think of it that way as well, right? Or it's some type of a I kind of leave it open. It can be anything, but if you think about it, it can be the latent variables form a Markov model, and I'm observing something with some noise, maybe. It is a Gaussian emission case. So this is quite abstract, obviously. Therefore, I included an example, but we will not solve it. We will just go through it to make things a bit concrete. I took it from this thing, and then also put the link here so you can read it even in more detail if you wish. And also included this slide that explains everything from Barber's book, the book by Barber. That's the same story, but told in a different way. I thought, it's also good to give you another version of it. So it's the same story. You have the same equation. You have the transition distribution, and you have the emission distribution. In this case, the emissions are V's, hidden variables are H's. Well, H is a good name for hidden variables, hidden states. So you have the H by H transition matrix, so that tells you how these hidden states are evolving. And then, of course, it doesn't look like a linear graph. It can be any graph, right? For the Markov chain, this is just a representation here. And then from any state, you observe something, H to V, and that is the emission distribution, probability of V given H, right? That's the conditional probability. Before I ask whether this is clear or not, let me give the example. And maybe after the example, things become a bit clearer. So let's do an example. There is a Markov chain. This is the hidden latent variables, right? Let's keep it as simple as possible. We have two states, hot and cold. This comes actually from botanic, not another real engineering example, or you can think of it biomedical if you want example. So the research from investigating the plants says the trees grow when the weather is hot. Trees grow more when the weather is hot, and therefore when you look at the intersection, if you look at this section of a tree and look at the rings are bigger when there is the temperature is more warmer, because the tree grows more. So the hot weather and cold weather, maybe these are the seasons over some time, then maps to the ring sizes, 3 rings of the trunk. Then and let's classify them to small, medium, and large, right? So in this case, the hidden variables are the weather, because let's say you don't have access to the weather records of the location of the tree, but you can actually look at the rings, count them, gives you the age of the tree, right? Each year 1 ring, and then you can look at the sizes of these rings, small, medium, and large. So the observation matrix is then this. So it maps the hidden variables, hot and cold season, to the ring size. This is a probabilistic system. It's not deterministic. It doesn't mean when the weather is hot, you get a large ring. So no, there is a probability involved. Maybe there are other factors. We capture them with a probabilistic approach. So this is the emission matrix that says, if the weather is hot, then it will be with low probability, it will be small. with almost equal probability it will be either medium-sized ring or large ring. But when the weather is cold, then there is a high probability that the ring size will be small, and then a very low probability that it will be large. Makes sense? So the hidden variables are then the H and C. And then this is the Markov chain of the hot year followed by a hot year, maybe, hot year followed by a cold year, and so on. So you can think of it like that. It's a very simplistic model. Then if we assume an initial probability and some observations, let's say we have 0, 1, counting from 0, that means I have a small ring and a medium ring and a small ring and a large ring observation, 4 observations. So the whole process is like this. So you have the states going through x0, x1, x2, right? And then from each state with the dependence of the emission matrix, observation matrix, we get the observations. Okay? So this is essentially the model that makes it concrete. So this is just the toy model, one of the simplest I can think of. You can make a very complicated hidden variable model and then the emission model observations. All right? So, okay, I have a hidden Markov model. Then what, right? So there are actually, to give you a high-level overview, I'm not going to go into, as I said, into details, but you can go and read this from the books that I've linked and mentioned. So there are actually 3 problems, 3 canonical problems with these HMMs, when you have a hidden Markov model. The first problem is all of them are very common sense problems. These are the questions you would ask yourself, right? Given the model, the first question is also maybe the most basic one. Given the model and the sequence of observations like this, so I am given a model and I'm giving certain observations. I have a tree trunk, and then I kind of look at the sequence of the rings of their sizes, right? That creates my sequence like this here. And then given these, what is the probability of the observed sequence given the model? So I observe something, but is that sequence a very common sequence, or is it a very rare sequence? What's the probability of observing that sequence? Is it a miraculously, strange tree, or is it a very common off-the-shelf tree? If the probability of observation is high, then it's a very common observation, right? So that's a common tree that has grown in certain way based on the hidden variables. So this problem, I will formulate this problem and give the algorithm without, again, spending enormous amount of time on it, just to give you an idea how things look like. So let's just define lambda as the model parameters. So we have the hidden Markov chain of the latent variables, A. Then we have the emission matrix, B. That represents the Markov chain from the observation matrix from hidden variables, latent variables to the observations. And then pi is the initial probability distribution. So we have this model, and then let's say we have a sequence of observations 0 to t minus 1, a capital T number of observations, a finite sequence, right? So what is the probability? Now we need to write in equations what we have said in words. So what's the probability that I have this sequence given x and lambda? Right? So the x is then the, we have been saying the x is the states, right? Is the states. So the outputs given the states and the system model is the bx0 of theta O0, the output of output 0, output 1, output t minus 1 in terms of the emission matrix entries, right? So, but what does the probability of x given lambda mean? Then that is the evolution of the hidden state. So this is the multiplication of the x's, the observations, x were the observations. Now this is the x given lambda is the evolution of the hidden state. So initial distribution, then the transition probability x0 to x1, then the x1 to x2, xt minus 2 to xt minus 1. So these with all these state evolution then from certain states. Then if we want to write it just in terms of the system model, remove the conditioning, we just sum it over x. That's the basic probability, right? So, and then that would be then P of x given lambda, summed over x, that's the to obtain the marginal, and then we can write this joint probability using the, the product, the rule. I can write this joint probability as P given O given x lambda times P x given lambda. Then that will give, by definition, very, very basic probability definition, the second line. And then when I substitute these entries, I get this whole product, right? So computing this probability over all possible x's is very expensive. So you can actually write this down, and then if you have enough computing power, you can compute this. But this is not the best way to do it at all. We have written what we want, the probability of observed sequence given the model. Indeed, in terms of the whole properties of the model, emission matrices and state evolution entries, A's and B's are the entries of the A and B matrices, and the observations sequence. But then this is very, very computationally expensive. So people came up with this very nice forward algorithm based on the, again, using the underlying Markov property of the process, right? So, and then this is the algorithm. I just give it to you quickly here. Just wanted to include it. So what you do is you define an alpha ti, and that's the probability of all the outputs, joint probability of all the output sequence, comma, the xt being qi, the t for time t, stage t. So you look at all the observations up to time t, and then if the state at xt is some qi, that will then be given the model. Of course, everything is conditioned on the model, as I was saying before. So you have defined this alpha ti, right? So, and you start with an alpha 0i at the 0 instance, the beginning. Then this is pi times bi o 0. So that's the probability of getting O0 out of this initial probability distribution. And then it turns out, I will not give the proof here, you can see it in Bishop, and also other places that I also mentioned where the example comes from. So you can actually compute this alpha ti iteratively in terms of alpha t minus 1s. So you have alpha ti for all I, that is all the states I equals 0 to n minus 1. N states, not because t is the time index here, I is the state index. So for each state and at a given time t, you can actually compute all of these n of those alphas in terms of the n of those alphas in the previous time instance. So you start from alpha 0, you go to alpha 1, n of them, and alpha 2. You see the dependence is directly through this equation. So you can iteratively find them, and when you come to the capital T, the last point of the sequence, then probability, as we have said before, this probability is the marginal of this, and then because it is the marginal of this and the definition of alpha, actually it is just summing up over the x's, all of the states, over the i's, and then at time t minus 1, which is the last time instance because we started counting from 0. So this forward algorithm is much more computationally handy than and it's a recursive computation compared to trying to compute this naive expression that we have derived directly from the probability rules. So that's, there's a bit more to the story, but yeah, I have given you the algorithm to answer the first canonical question. What's the probability of the observed sequence given the model? Even more maybe interesting questions are, given the model and the sequence of observations, what is the most likely hidden state sequence? So that is also an important question. So I have visually, if I observe if I observe V1, V2, V3, V4, for example, what's the most probable hidden sequence H1, H2, H3, H4? I may never know them, right? But I can make an educated guess based on the model. What is the most probable latent variables sequence that has led to my observation? So it's a maximum likelihood, again, idea. And the algorithm to solve this is the Viterbi algorithm. All right, so I'm not going to go over it, but you can use the Viterbi algorithm to find the most likely hidden sequence for your hidden Markov model. And the third question is, given the model and the sequence of observations, how do we find the most likely parameters of the HMM? Now, I have the model, I have the sequence of observations, then can I estimate the parameters of the hidden Markov model that has generated this sequence of observations? And that's solved by the Baum-Welch algorithm, or it's an instance of an expectation maximization scheme. We have covered expectation maximization before, right? So 3 main questions, 3 main algorithms, classic algorithms to answer those questions. And that's kind of practically what you need out of a basic understanding from a hidden Markov models. They were very popular. So they were the big game in town before all this deep learning stuff. So hidden Markov models were the main, for many of the classic tasks like speech recognition, synthesis, because they are generative models, right? So you can generate some sequences out of them, observations once you have a model. Then translation a little bit. So all that stuff. That was done with hidden Markov models, because the idea is you have a sequence of observations. Most of the time there is something going on behind the scenes, and this whole latent variable state state space, and then the Markov, and then the building a Markov model of these latent variables makes a lot of intuitive sense. Then I say here's a model behind the scenes. Then I kind of define how the model emits what I'm observing, and that gives me the picture. All right. Any questions regarding that? So my goal has been, by covering this, my goal has been to give you some initial kick. What is a hidden Markov model, and if you want to use it and read more about it, I wanted to empower you a little bit on that rather than skipping it. So I hope that achieves the goal, gives you a big picture, because then the rest is going to the details. What you can do rest is you can actually look at the algorithms, look at the derivation of the algorithms, for which you only need probability theory essentially. And then they are iterative algorithms most of the time. And you can actually then download the software package and play with them. I haven't included in the workshops, but maybe next year I can include it. So that's a lot of classic stuff on hidden Markov models. Any questions? Useful? Or should I delete all this stuff next year? Okay, some say we'll find out. Okay, yeah, let me know. Like, I think this is better than nothing. In that sense, it should be useful, I'm hoping. Gives you a guidance. Next comes the linear models. Now we are coming, this is the probabilistic view, and with the Markovian point of view, you can look at the sequence, time sequence. Another way to look at the time sequence is with the linear models, and this is very, very much touching digital filters. That's I'll talk about a little bit of signal processing here, right? So how does it work? Let's talk about filtering. So the simplest method is moving average, right? So you can take a window and do a moving average filtering of the data. So it's done a lot on for example, finance data, right? Or any noisy type of data from economics and finance. People try to get rid of the noise by doing a moving average. But if you have taken any signal processing, digital signal processing, you have done a little bit of that, right? In signal sense systems, you know that this moving average is actually a low-pass filter. So essentially, you're doing a low-pass filtering with the window here. And that's the basic low-pass filter. Then you can do a weighted moving average. So that is, you can do a low-pass filter by putting weights, beta weights, to your elements, and then filter like that. So that will allow you to give different weights to some of the closest. Maybe the most recent elements get more emphasis, and the others you forget slowly the ones that are more in the past. Again, it's over a window, and because you are looking kind of up to m minus 1 to the past, k minus I here. So you have a fixed finite past window, and you're doing a sliding window essentially over the sequence. And then exponential moving average is actually doing an infinite pass, but then it's a very standard method. So here y appears on the right hand side, right? So it's in that sense autoregressive model, and then there is an alpha that's less than 1. So you forget the old ones pretty quickly exponentially. So you take them into account, but their effect diminishes as time goes by. All right, so that's the exponential moving average, weighted average. You can do also weighted average, weighted version of that as well. So that's something we can do, right, with our sequence. So the question again is like the hidden Markov model, but can I create a model, or can I have a model to analyze this sequence, just like we did with the Markov model? That was a probabilistic state model. Here we can come up with certain type of a model to analyze my sequence, and that is one of the most fundamentals is the autoregressive model, right? So if I have xt, then if the xt depends on xt minus 1 to xt minus 2 to up to xt minus p plus some noise term, right? So that's and then each of them have a parameter in front of them, alpha 1 to alpha p. So if I identify alpha 1 and alpha p, then that would be kind of a representation of my sequence, right? So this can be also written nicely like this, xt as a sum, right, over a window of p, and p is the model order. So of course you make it bigger, you have more parameters, the more complicated it gets. It's the similar story in terms of model complexity that we have been talking about. So actually using the systems terminology, remember we were using z to the minus 1 as the delay. So therefore, in discrete time, you have done this, right? A while ago, in signals and systems. Who said no? Because I've seen the final exam of signal systems recently, and it is there. How did you pass without that? It was there. So z to the minus 1 means t minus 1, right? So if you take the z transform, or only use it as a representation, as a delay element, so you can write it this way, right? So then if I take this to the left, you have 1 minus all these z to the minus I, and then that's equal to the right-hand side. You have this random process input, or you can write it this way, right? So you have this equation. So this is actually an infinite impulse response filter, if you know what I mean, IIR filter. And the reason for that is if you write it, something as 1 over 1 minus x, you can write it as an infinite sum, right? So therefore, we can write this, because this is an autoregressive, everything is in terms of x's, you can write it as this 1 over 1 minus this similarly can be written as an infinite sum with different parameters, not alphas, but betas. And how you derive alphas from betas, there is literature on that. You can actually show that, take this and then write some betas, where betas are functions of these alphas, as an infinite sum. But then this shows that why this is an infinite impulse response filter, linear filter. And it's a linear system, it's a linear filter, right? So you have no nonlinearity here whatsoever. The other thing, actually, this is what you have been doing in the workshops, right? So you have the workshops playing with this autoregressive model, but there is also an extension of that is autoregressive moving average model. So that is the case where you have the autoregressive part and then moving average part together. But it is important to note that this moving average model this is a stochastic model, and it's different from this moving average, taking moving average of a sequence. Taking moving average of a sequence is a different thing, and this is a different thing. Here you have a stochastic model because there is an input random zero mean random process. For example, it could be white noise, epsilon, and then that passes through with some delays and multiplies with the beta parameters, creating as an output of xt, and then that output is combined with the autoregressive parts output. They two together make an autoregressive moving average model. So essentially you combine two models just with a simple addition, autoregressive part and the moving average part. So then this is called a PQ, is the model order. P is the autoregressive parts, Q is the moving average part. You have been doing this, or you are currently doing this, right? So in the workshop 3. So this is kind of a, I haven't given even theory, but this is the framework, model framework of what is going on here. Just like that hidden Markov model, Viterbi algorithm gives me the parameters of the model. What would be the counterpart? How am I going to find the alpha beta, right? So that's the, actually, you can use Yule-Walker. Actually, if you have only an autoregressive model, you can use Yule-Walker equations. And if you have a joint model like this, you can simply use a least square method to find the ARMA parameters. You do essentially you solve an optimization problem, and then given your sequence, you kind of give the sequence and then look at the model outputs in terms of alpha and betas, and then you do a mean square error, and then you minimize that mean square error, you'll get the alphas and betas. Very, very, very meaningful, right? So that's what the software was solving behind the scenes. There are different also solution methods, but the main idea is this. So you are given a sequence, and from the sequence, I map that sequence to this. I fix the ARMA model, choose the model, then I choose that optimization problem gives me the most probable, the alphas and betas that are giving the least error. And every caveat applies. I have a training sequence, then I get the alpha beta from the training sequence to find the minimum error, and then they gives the best estimates of alpha and beta vectors. Of course, I need to test it on the test set, otherwise it doesn't make sense. You can overfit it and underfit it. The same ideas apply. You can choose the order too large, then you do an overfit. You will do worse on the test set, and then you can actually underfit it, then you will do more error. And what is the test set actually for a sequence? The test set is, well, how are you going to do in the future, right? So you can divide it. You can take the last part out of your sequence, train it on the previous part, and then use the last part to verify as a test, right? So if it's a year, maybe you take away the December and then train on January to November, and then estimate the December data. Of course, if there's seasonality, you shouldn't do that, but assuming there's no seasonality. Or you look at the last 24 hours and estimate the next 24 hours. I think that's what I gave, right? For power estimation. It was in this workshop. Or was it the one before?
The houses thing?
Sorry?
That's the power estimation of the houses?
Yeah, I think that's
Quite half and half.
no, I mean 24 hours to 24 hours, right? It was 48 half an hours and 48. Yeah, that's what I remember. Doesn't matter much, but yeah. I wanted to look at the previous day and then estimate the next day. So that's kind of a legitimate forecasting problem. And then using last year's some previous data, historical data. I again put some links here if you want to read a bit deeper. And again, if you notice, I have skipped some of these algorithms, right? But then I have told you where the algorithms come from. Like that's, I'm hoping that towards the end of the subject, you are reaching slowly towards that maturity. That once I tell you the main story, what's going on, main question, main aspects, you can go and find it. Because essentially, this is the last step. After this, unless you do a PhD, you go outside, and this is what you're supposed to do. You should be, as a good engineers, you should be aware of the topics, main idea of the topic, and then, someone says, here's a problem, and then maybe it gives you guidance. Why don't you try this method? You should be able to get the relevant software, have a quick read of what's going on theoretically as well. Otherwise, you'll end up in a bad avenue. and then just use it to solve the problem as an engineer. I'm kind of trying to go towards that direction, to be honest. Okay, any questions at this point? You had these slides already, so sorry for the delay, but at least the slides were under your hand and with all the links and so on for the ARMA. So I thought it would be good to keep that. I was going to jump directly to the neural networks, the modern deep learning methods, but as I say, a lot of youngsters these days jump to the most shiny methods without thinking about it. The linear methods like the ARMA is your baseline. You know, when you even do for a practical project, I would do a maybe linear model just to get an idea what's going on, and you know, and then you can say to your boss, oh, by the way, I have found this another method that outperforms ARMA model so much. Like you can also say that, right? So that's an option. So recurrent neural networks. Now we come to the very exciting topic, to be honest. Much more exciting than the regular feed-forward neural networks. And this slide hopefully explains why, this slide and the next slide. So it is also interesting to teach you this because you're electrical engineers and you know system theory. Don't underestimate the power of system theory, and you're very lucky knowing that. You know, most computer scientists don't know system theory, and it shows in terms of the depth of understanding. So you will see it now. So all the neural networks we discussed until now were the feed-forward one. We have discussed only one type anyway. They are function approximators, right? Universal function approximators. There is an x input and y output, and then when I train my network, then y of t, the network will be g of xt as the input, and after I train, I will know the theta parameters of the network. These will be the weights. And then everything is nice. So the y of t, once I give x of t, the network will tell me y of t. I have a nice nonlinear function, right? But they are instantaneous. So they are only functions. A function doesn't have a state, right? So they don't have a state. So the feed-forward network doesn't have a state. There's input, goes through the layers, and you get the output. I mean, of course, it takes milliseconds. It's actually a pretty fast process. So you don't have a concept of a state. So, but if we have a dynamical process over time that generates sequential data, and then you know what a dynamical process is, right? So, for example, this continuous linear time invariant system. So that is have you seen this in the control, or in the signals and systems? Signals and systems, at least, yeah. So this is just a this is a continuous LTI system, right? Why is it linear? It's a linear system, therefore it's continuous. X is continuous, Y is continuous. Linear, obviously, these are all matrices and vectors. Then time invariant means these matrices don't change over time. A is A, B is B, right? Just like our ARMA model. Our ARMA model is also time invariant and linear, actually. Look at this. X is actually our state variables. This is almost like these latent variables. And Y are the observations. Those are the observations. So you see the same mentality that hidden Markov model is a probabilistic finite state counterpart of this guy. So you have, in the hidden Markov model, you have the hidden states, latent variables, they were Z's. And then in that notation, the emission, what I'm observing, then the counterpart of that will be the observations Y in this model. X is mapped to Y, and then you may have a control about it as well. U is the control input, then U will be the input. So the dynamical process doesn't have to be linear. It can be also nonlinear, right? So actually, it is a time invariant system. If I define the state as S, without any control, let's keep it simple and forget about the observation. Just focus on this part, x dot equals AX. That's the linear thing, and this is the nonlinear thing. So f of st minus 1. So the previous state defines the next state with then mapping, nonlinear mapping f, and theta is the parameters of that mapping, right? In this case, for example, if it's x dot equals ax, a is the theta, then f is the ax, right? The function, the matrix multiplication is the f, then x is the s, right? Or if you have an input or control, then actually in this case, the notation It messed up, but like X here denotes then the input, because S is the state, right? So this is the control, and then this is the from the deep learning book directly. So just you need to map the input to state and input to the parameters of to different versions in your head. So, but this is still state space. We have still the same powerful concept of a state. Like the next state is only determined by the previous state. So the whole idea of current state summarizes the whole history is still there, right? All right. So that is the important part. And now I'm going to show you something quite surprising. So most of these things you won't see in computer science books, because computer science people don't know system theory. So when you go read something about RNN, you will not see this connection to system theory, because the audience will not know, they don't bother. So in that sense, it was a pleasure to prepare this slide for me. So yeah, and if I were teaching to CIS, I wouldn't be able to include this slide, because they wouldn't know the signals and systems subject. Okay, so the idea is then the neural network is very interesting. Here's the idea. We use hidden units of the neural network to capture state. That's the idea. All right. So maybe I should make it red. That's the idea here. We use the hidden units of the neural network to capture the states and represent the state, and that's done by this evolution h. T is function of h of t minus 1, an input and the parameters of that mapping f. But then this can be this, all the books talk about, deep learning book talks about this unfolding. It is nothing but a dynamical system. This whole unfolding business is teaching dynamical systems to people who don't know any system theory. So all you have is this basic nonlinear equation, which means you have the one unit delay. F is h of t is function of h of t minus 1. So h is the state variable actually, if you know state idea. So this is actually a time invariant state space model, and then this is the invariant function implemented by the neural network. So we have then if we write it like this as a general expression, h of t is g of t depending on all the previous values. Instead, if writing the hidden state in terms of all the previous inputs, x here is the input in this notation. I'm following the deep learning book's notation. So therefore, all of the previous inputs will, of course, determine the current state, but I can write it as a nice state space equation, nonlinear state space equation, and this f will be my neural network. So that is the core idea of a recurrent neural network. All right, I think I ran out of time, but that's okay. We have still 5 more lectures and 1 guest lecture, so I might use a little bit of the next week's lecture, finishing the RNN and CNN, then go through the reinforcement learning, and then which I will post, give you a good overview of reinforcement learning that's supported by workshop, and then we will close, of course, the discussion. All right, so yeah, this time, right? So don't want to take the next hour. Thank you very much, and have a nice weekend. I will post the submission for the workshop 3.
I just want to ask, are there any possibility that we can have the feedback of workshop 1 and 2? Or like
No, actually, I was going to mention it, sorry, the workshop feedback. There is actually feedback with workshop. Just ask your demonstrator.
yes. But,
So they are supposed to put some feedback to
to the report, right?
the report.
Sure.
Minor feedback, and actually if you want to have a bigger discussion, again, that's the person to ask.
All right.
So, like there must be somewhere in the LMS. One of them told me he will give directly. Some others they said they put the comments to the PDF. Some other.
Right.
So there are multiple options. If you cannot find it, don't bother. Just ask them.
Okay.
Ask your demonstrator for the feedback.
So are we getting the like a answer, like a correct answer of the workshop?
No,
No. Okay.
but because it's all wide open,
Yeah.
so
I see.